Hi everybody, this video is going to be on section 10.4, which is called Areas and Lengths in Polar Coordinates. So the idea here is, can we do the area inside of a curve and also lengths, but instead of using regular coordinates, to use polar coordinates? Okay, so we're going to start with a polar function. Okay, so let's begin with r equal a function of theta, right? So in other words, we have some sort of a curve, and what we want to do is we want to find the area not under the curve, but we want to find the area bounded by that polar region, right? So if this is theta equals A, I'm sorry, let me not write A here. How about alpha? Theta equals alpha, and here theta is equal to beta, and this is r equals f of theta. We wish to find the area swept by the polar curve. In other words, we are trying to find the area that looks like this. Okay? So we cannot use old notions of area under curves to do this, right? We're not going to be building we're going to be building a Riemann sum, but not with Cartesian rectangles. So what we want to do is, the concept behind what we're doing is we want to use polar rectangles to split up the area. Okay, so to do this, we need to recall a few things about geometry. So first of all, I want us to recall that the area of a sector of a circle so if the sector looks like this, so this is theta and this is r, then the area inside of there is equal to 1/2 r squared theta. Okay, 1/2 r squared theta. Okay, so here's the idea. Okay, the idea is that normally we partition x, right? So normally we partition x. If this is A and, sorry, this is B, then we partition it. If we call that x0, then this is x1, x2, and all the way down to xn, right? xn would be the last one. And then we take underneath and we approximate this with rectangles, right? And so on. And then we can add up all the areas here. So we're going to do a similar process, except we're going to partition now alpha to beta into n subintervals. With equal width. And we're going to call the widths delta theta. And so each partition then, they're going to look like this: theta 1, theta 2, and we start at theta 0 would be the first one, and this is going to go all the way down to theta n. So what are the partitions then? The first partition is theta 0 to theta 1. The second partition is theta 1 to theta 2. And we do this all the way down to theta n minus 1 to theta n. Okay, so here's my picture. I'm going to make this really big so we could see it, okay? So, maybe the first partition looks like this. And then the next one looks like this. And then the next one looks like this. And then the next one looks like this. So what we're doing here is we're splitting it up. And this would be delta theta. This would be delta theta. And so on, okay? So this is, if we were to label these with actual names given what we've seen, this is theta is equal to alpha, but we call that theta sub 0. Okay? The next one, this is going to be theta equals theta sub 1, theta equals theta sub 2, and this goes all the way down, and the very last one, of course, is theta equals beta, which we're going to call theta sub n. Okay, now we're going to isolate, we're going to restrict our attention to the ith one. Okay, so here's what we're going to do. We're going to take one of these guys and I'm going to zoom in, okay? I'm going to zoom in on this guy right here. And I'm going to zoom in on that on a different page, okay? So what we're looking at here is just that guy, okay? Okay, all right. So there's that guy. Here's the idea, right? This is going to be theta is equal to theta sub I minus 1, and this is going to be theta is equal to theta sub I. Now, before I say what we're going to do here, what we want to do, just like before, when we were doing Riemann sums, we need to choose a representative, right? And so let's say, for example, that you have an xi minus 1 and an xi, and your curve looks like this. What we do is we choose a representative inside here, which we call xi star. And that gives us a point on the curve, and then we use that representative to determine the height. And that is what we pretend that this is a rectangle of that height the entire time. We call that a sample point. So what we're going to do is we're going to choose a representative, or you can call it a sample point if you want. We're going to choose a representative theta I star, and that's going to be inside of that subinterval, theta I minus 1 to theta I. Okay, and let's go back here. Let's say I choose the midpoint, okay, just like over there. So this is going to be our theta I star, right? So this is theta is equal to theta I star. Now, what we're going to do is we're going to take that point right there and we're going to pretend like the radius r is equal to that the entire time. So this is what it's going to look like. Now, I know that we happen to choose something that looked like the minimum. That was a coincidence. But the point is, just like we pretend like this is a rectangle the entire time of that height, we're going to pretend. So here, we basically take y and we set it equal to f of xi star the entire time, right? It's a constant. We're going to do the same thing here, right? We're going to take r and we're going to set it equal to whatever the function of that representative is, right? So we take that guy and we make r like that everywhere. And so isn't it true that we can approximate the area inside of here? So what would the area of this ith piece be approximately? Well, if we use that representative, remember this formula that we have a couple steps back, we know that it's equal to 1/2 times the radius squared times theta. So the idea is we're approximating it with this sector. So the area is approximately equal to 1/2 times f of theta I star squared. And then remember, this entire part right here is delta theta, right? So this would be times delta theta. So what would the full area approximately be? So the idea is we do this many times, right? We've got a sector here, then we've got a sector here, then we've got a sector here, and then we've got a sector here. So what we're doing is we're going to use the area inside of all of these things to approximate the area in the curve. Okay, so that's what we're doing. So this means that the area is going to be approximately equal to the sum. We're going to add up from 1 to n of 1/2 f of theta I star squared delta theta. But then that means that if we want to make this exact, all we have to do is take the limit as n goes to infinity, right? Which means that we're actually splitting this up into smaller and smaller pieces, just like the smaller rectangles approach the area in the old integral. This is actually going to approach a different integral. So what does this equal? This is just going to be the integral from alpha to beta of 1/2 times f of theta squared d theta. So this is the area. So this is the area swept. It's not the area under the curve. Remember, it's the area swept by the curve r equals f of theta when theta is between alpha and beta. An easier way to remember this formula, by the way, is we just remember it this way, r squared d theta. And just remember that your r is this function, okay? So if you remember that r is the function that's given to you, then this would be how you would remember it. So we're going to practice some examples where we actually use this. Let me just give a quick hint really quick. So hint or tip, a loop, something interesting about loops in polar curves. A loop in a polar curve are values, I should say a loop starts and ends where r is equal to 0, right? So I want you to think about any loop, right? Anytime that you have a loop, for example, here's a 4-leafed rose. We did an example like that before. Anytime you have a loop, because a loop begins and ends where or at the origin, that's exactly where r is equal to 0. So this means to find the area inside one loop, which problems sometimes ask you to do, what you want to do is you want to find consecutive values of theta where r is equal to 0. Okay? It has to be consecutive, right? Because if it's not two that are next to each other, then that means you might be counting more than one loop. So it has to be, for exactly one loop, you need values of theta that come right after the other. So I want us to do an example using the four-leafed rows from before. So this will be example 1. I want us to find the area enclosed by one loop of the four-leafed rows r is equal to cosine of 2 theta. Now, contrary to what you might think, we do not actually need to sketch this graph in order to be able to determine the area. I mean, we've already done this in a previous example, but we don't actually need that, okay? So what we really need to figure out is what values of theta start / end a loop. Well, we could use the trick that we learned in the other section. We could write it this way, and we know that this looks something like that, right? Each of these is a loop. I'm going to write here, this is a loop, this is a loop, right? Because when r is 0, that's actually the origin. So these actually represent loops. Now, we have many potential integrals that we could set up, but I'm going to use this loop right here. And so remember, this guy is pi over 4. You could easily figure that out, right? And this guy right here is negative pi over 4. And you could test that by plugging pi over 4 and negative pi over 4 into this, right? If you plug in pi over 4 into here, plus or minus pi over 4, of course, you will get a 0 here, right? So we know that this is going to be the beginning and end of a loop. So remember, the area, what we just learned, is the integral from alpha to beta of 1/2 r squared d theta. So let's actually plug in what we know then. We're going from negative pi over 4 to pi over 4 of 1/2 times the radius is cosine of 2 theta squared and then d theta. How do we actually do this integral? Well, we can double it and go from 0 to that value. And then we can also use half angle. Let me remind you guys of the half angle formula. Cosine of 2 theta, remember, cosine squared of 2 theta, which is what we have there, is actually equal to 1 plus cosine of 2, it's going to be 4 theta, right? Because we have to double it, divided by 2. So if we pull that 2 out, and we're also going to double it and go from 0 to that, so I have the double. I'm going to pull the 1/2 out, and I'm going to pull another 1/2 out. And I'm going from 0 to pi over 4, and then I have 1 plus cosine of 4 theta d theta. Now again, please don't be confused. This 2 that you see in front is because I went from 0 to pi over 4. This 1/2 is the 1/2 that was already in there, and then the second 1/2 is from this identity, okay? So all the 1/2s come from somewhere. So the 2 cancels out the 1/2, and I still have a 1/2. What do I have left in there? I have a theta plus, and then the integral of cosine of 4 theta is 1/4 sine of 4 theta. And we're going from 0 to pi over 4. If we plug in 0, everything's 0. If we plug in pi over 4, the second term is 0. So we literally just have 1/2 times pi over 4, which is equal to pi over 8. So there you go. We found that the area enclosed by one of the loops is actually pi over 8. What's so interesting about this to me is the fact that if that's one loop, then this means that 4 loops actually gives you pi over 2, and pi over 2 is half the area of a unit circle. So what we actually just learned as a geometric thing is if you have a unit circle and then you have this 4 looped rows that sits in there, what we actually find out from this is that the 4 leafed rows actually makes up half of the entire unit circle exactly. Of course, I did not draw this picture to scale, but it's still an interesting notion, right? Anyway, that's an example of using finding an area with polar coordinates. Let me do a trickier example. The next one I do is going to be quite challenging to set up here. I don't want to actually solve the problem, but what I want to do is I want to set up an integral. That can be used to find the area inside both polar curves. So these curves are going to be r is equal to 3 sine theta and r is equal to 1 minus sine theta. Now, this one's going to be a lot trickier, right? Because we're talking about the area inside 2 curves, so we need to actually draw a picture. It's almost like a Venn diagram, right? We're trying to figure out the part that sits inside both of them. Okay, we already know what r equals 1 minus sine theta looks like. What does r equals 3 sine theta look like? So this guy is the same as r squared is equal to 3r sine theta, which is the same as x squared plus y squared is equal to 3y. So what is this? You know what? I'm sorry. Let me change this problem. Let me make this a 2 so that the math works out a little bit better. I don't want to have to deal with fractions here. So let's just make it a 2. So that's a 2. So then if I complete the square, I just add 1 here. And I get x squared plus y minus 1 squared is equal to 1. Okay. So what is this? This is a circle with radius 1 centered at 0, 1. So let me draw the curves in 2 different colors so you can see it, okay? First of all, I'm going to use red to do this one. So it's going to look like this. Sorry, that looks like a terrible circle, but that's our circle. All right, we're going to use our imagination here. This is a circle of radius 1 centered at 0, 1, right? And then I'm going to use a different color. Let's say I'll use blue for this guy. So in blue, remember we had our cardioid from before, and so it looks something like this. Right? And so the part that's intersected by both of them is the stuff I've just shaded in, right? Now, even though I didn't draw it that way, we do have symmetry here. So really it's only necessary to find one of the 2 sides. So what I'm going to do is I'm going to focus my attention on the right side here. Now I want you guys to notice something, okay? I drew them in 2 different colors so that we could be clear and understand that the red curve right, r equals 2 sine theta, is actually what's sweeping out the beginning part. And then the next is by the other part. So actually, let me back up a bit. What I want to do is actually I want to shade this in a different way. So let me go to the next page here. What's actually happening, if I were to use my same two colors as before, let me see, I had blue on top, red on the bottom. So if I was using the same colors as before, it would look like this, right? I've got blue on top, and then I've got red on the bottom. And so what's actually happening is the red curve is sweeping out one part of the area that I want, and the blue curve is sweeping out the other part of the area that we want. And I'm going to, r equals 1 minus sine theta is this guy. And then the other guy is, remember, r equals 2 sine theta, right? So the key here then is actually going to be to figure out what the theta value is for the first and then what the theta value is for the second. So we need to actually figure out where these two guys meet each other. So where do they meet? What is this point in question? I know I drew it so that it looks symmetric, but the left and right side are not necessarily the same, right? I mean, we've got a circle and we've got this other guy. It could be more something like, something like that, right? So it doesn't have to be exactly symmetrical. So here's how we figure it out. What we want to do is we want to take those two curves and set them equal to each other. If we do that, we actually end up getting 1/3 is equal to sine theta, or theta is equal to arc sine of 1/3. Okay. So for the red part, so I'm gonna actually have two different parts, right? I'll call the red part A1, and then I'm going to call the blue part A2. So what's A1 going to be? Well, I know that I'm going to integrate from, so here's the thing, right? When you look at 2 sine theta, when you plug in theta equals 0 for this guy, theta equals 0 is the start of the origin, right? And we know that we're going to end up here. So that means we're going from 0 to arc sine of 1/3. And then this is going to be 1/2 times r squared d theta. Plus. Now, everything we wrote there is going to give us the red shaded area, okay? Now, what about the blue shaded area? Well, we need to figure out where that guy, so coming back to our picture, we need to figure out what the blue theta equals in order for it to hit the origin, right? So for the blue part, this value right here is when theta is equal to pi over 2. And you could check that, right? If you put in pi over 2 there, you actually end up getting an r of 0, right? So coming back to here, this means that our blue integral is going to go from arc sine of 1/3 to pi over 2. And then we have 1/2 times that radius squared, so that's 1 minus sine theta squared, and then d theta. Neither of these integrals are hard to do. You just use half angle formulas to do them, since you're going to get a sine squared theta here. So it's not tricky, but all I wanted to do was show you guys the setup. This this is a tricky example, so I wanted you guys to at least see one hard example here of areas inside of two curves, for example. Now, the last concept we're going to talk about with polar coordinates is arc length. You guys remember arc length. Okay, arc length, when we first learned it, remember we knew it was equal to the integral of ds, right? And we knew that meant, when we first learned it, we knew that meant the square root of 1 plus dy dx squared, right? This is when we wanted to integrate it with respect to x. Then we learned in our parametric section earlier in this chapter that if you want to do it with t's, this is going to become dx dt squared, and then this is going to become dy dt squared dt. So all of these are equal to arc length. But question, what's going to happen when we want to use polar coordinates instead? Well, we know that this is actually just going to be dx d theta squared plus dy d theta squared, because our parameter now is theta. So it looks like this. Okay? Okay. Now, what do we do here? Well, we know what dx d theta is. Remember, x is equal to r cos theta. Y is equal to r sine theta. So remember, dx d theta is equal to, let me call it this, r prime. Remember, r prime just means dr d theta, okay? R prime, I'm using the product rule, cos theta, and then minus r sine theta, and then dy d theta is equal to r prime sine theta plus r cosine theta. So the idea is that if you take this guy and plug it into here, and you take this guy and you plug it into here, we're going to get a lot of simplification, okay? And indeed, I'm going to save us the algebra, because if you plug those things in, what you end up getting is that this is equal to the integral of the square root of r squared plus its derivative squared, and then d theta. Okay, and so essentially what we're saying is that ds becomes the square root of r squared plus dr d theta squared, and then d theta. So this is something useful to remember. So in other words, the old arc length formula works as long as you remember that this is our new ds. So how would you do, for example, this will be our last example, how would you set up an integral that can be used to find the arc length of the cardioid? R is equal to 1 minus sine theta, our favorite curve, right? Okay, so we know the formula, right? So what would dr d theta be here? Dr d theta is equal to negative cosine theta. Okay, so our length is going to equal, now I can integrate from 0 to 2 pi because I know that 0 to 2 pi gives us the entire cardioid, but I can also go from negative pi to pi, so I think that that's the easiest way. And it's going to be the square root of r squared plus dr d theta squared, and then d theta. I actually want to show you that, I know I said to just set it up and this is the setup, but you know, this integral is actually some nice algebra works out here. So if you notice, when you square that out and you square this out, this adds up to 1 under the radical. And so what you end up with is the integral from negative pi to pi of the square root of 2 minus 2 sine theta d theta. Or if we take out the root 2, and also we take out a double, I double and go from 0 to pi because, oh, sorry, not yet. I can't do that yet. I'm going from negative pi to pi of square root of 1 minus sine theta d theta. So this is how I'll leave the answer because that does look a lot nicer than what we started off with. Now, if you actually wanted to integrate this, a nice trick is to multiply top and bottom by the conjugate of this radical, and then you'll see that lots of nice stuff will happen and the radical will disappear. Okay? But anyway, this is how you do areas and arc lengths using polar coordinates. All right, guys, thank you so much for watching this video.